Hello, everyone, and welcome to our online training for students presented by Deliverable Software. Today, we will be working with our FEA and design software RFEM, and the goal of this training is to go over the fundamental knowledge needed so students can model/work with any type of basic structure, view results, and understand fundamental basic theories. In this training, we'll be focusing on mostly simple models. So my name is Alex Bacon, and I will be your trainer for today. I'm a technical support engineer, and I am joined with my co-organizer, Amy Heilig, who is the CEO of the US office and a technical support and sales engineer. We are located in Philadelphia, PA. So here is the control panel. This will be used throughout the training. And with this, you can show or hide the panel as well as adjust audio settings. There is a box where you can find the materials for this training, such as the training manual and models, the PowerPoint and models, and a link to our FAQ section of our website. There's also a chat box where you can ask us questions as well. Make sure this is set to organizers only. And this, I would also like to mention, this training is intended for you to just listen, but you can model along if you'd like. And I can't stop and help you with any specific modeling issues. But with that said, feel free to stop and ask me questions at any time as I'm modeling about RFEM itself. Also, Amy will interrupt me if she sees any questions in the chat or anything like that. There also will be 2 breaks throughout this training, one at a 5-minute break at 2 p.m. and another 5-minute break at 3 p.m. So about one third and 2/3 throughout the training. So here's the content for today's training. So first, we're going to start off with learning about the principles of FEA, and then I will go into an introduction into RFEM. After that, an introduction example will be done for continuous plates, and then I'll go through a stability analysis or Euler case 1 example, and then that will be followed with a moment frame example. And lastly, we'll end with a concrete model, and then I'll try to leave some time at the end for questions as well. So to start off, we are going to go through the basics of finite element analysis. So basically, computer programs or computer software is based on the displacement method. Another method you may be aware of is the force method, where the unknown is the force, and then you can calculate the internal forces based on this. With the displacement method, the unknown is the displacement of the structure or element that you are modeling. First, you can calculate the displacement vectors using the displacement method, and then the internal forces, and after that, the support reactions. Next, basically an analytical solution can be proven to be difficult with large complicated structures. So doing hand calculations for a large complicated structure can almost seem impossible, and the limits are basically being reached for this. So it is hard to yield accurate results, and this is where FEA is then required. So with FEA, the structure model is taken into the program and converted into finite interconnected element mesh. And then the material and the cross-section properties are given at each of these FE nodes. And then the mechanical behavior is transferred between each of these elements within the structure. I would also like to point out a good word to know is discretization. and this is basically when the structure submesh is being submeshed into finite elements. So I'd like you to walk away with this word. Now on to the procedure of FEA calculation. So step one is to determine, the program determines the local element stiffness properties. And then after that, the global coordinate system properties are the stiffness transferred to that. And then following that, the entire structure is assembled. And then the support conditions are implemented. Fifth, the displacement vectors are determined. And then sixth, the internal forces and support forces are determined. So now I think is a good time to start the continuous plate example. So you can see a continuous plate is modeled here. We have 3 of them. And then we're going to compare these results of the bending moment with this continuous beam at the end here. And I think this should be pretty interesting. So now we can jump into RFM. I'm just going to pull up RFM. And before we hop into RFM, I would like to pose a quick poll for everyone. And this poll is basically just asking if you plan on modeling along or not. And I'll just wait for everyone to answer, wait for the majority of everyone to answer. Okay, so it looks like the majority of everyone answered. So now I can share the poll. And so it looks like about almost half and half. Some are going to model along and some are not. So to answer your question, you can model along if you'd like or not. I just won't be able to stop and help if you have any modeling errors or not. But yeah, you can feel free to model along. I can take that into account with the pace that I go at. So now I will close the poll. And now you should see RFM. So basically, this is just a pre-modeled model that I'm pulling up right here, just so we can go over the basics before we start modeling. Another question I would just like to give real quick, just to understand everyone's skill level. I'm just going to give one more poll. And I would just like to know, how familiar is everyone with using RFM? Maybe some people have never used it. Maybe some people are very good at it. Also, a quick note, if you're not able to interact with the polls, this could be an issue with GoToMeeting, where you need to use the minimum or minimized version of GoToMeeting. Sometimes when you have it in full screen, this is a bug with GoToMeeting where you won't be able to interact with the questions or polls. Okay, awesome. Looks like mostly everyone has answered, so I'm going to close the poll. And I can share the results. And it looks like, yeah, between 1 and 3, some people don't know what RFM is, and some people have modeled it in every once in a while but still need help. So awesome. I'm going to hide that. And now we can jump into RFEM. So what is RFEM? Well, RFEM is a structural analysis software capable of analyzing plates, members, and also solids. And after modeling, you can run calculations, and this can give you deformations, stresses, and internal forces can be calculated on 3D structures. So almost anything is possible to be calculated, and this also includes volumes. So now we can go over the UI of this already modeled structure. So on the left-hand side here is very important. This you'll be interacting with, I would say most of the time. Most of the time you'll be within this work window, I would think. But this is what we call our project navigator. And this is where all of the model data is organized into these trees or subfolders. So you can see within these subfolders, I have, for example, my members right here. I have a members folder, and you can see that all of the members within this model are listed here. And you can see that as I click on them, this is synced with the graphical window. So if I need to find a member, I can do that easily over here. And you can see that the cross sections and member type are listed. Next, maybe if you've just downloaded and opened up RFEM, I have my tables hidden, but yours by default should be at the bottom here, and you can adjust the size of these windows if you'd like. These windows or this table can be used to, again, view the organized model data of your model, but it can also be used to create and give input data as well. So you can delete and create data within these tables. And you can see model data is one of the first tables. You also have your load cases and combinations, loads in this table, as well as your results. Next, we can move on to the most noticeable thing, which is the work window. So here in the work window, you can view your model, and you can see that I'm moving my model around, and I can do this. If your mouse has a scroll wheel, you can click down on your scroll wheel and you can move your model around in translation. And you can also hold the control key on your keyboard and click the scroll wheel at the same time, and that will allow you to rotate your model. And also the scroll wheel, you can zoom in and out of your model. Another thing to know, or maybe a useful hint, is up here in the options and in the configuration manager, you can change the background of RFEM from a white background to a black background if you would like. We also have other backgrounds here from Tekla as well. I'm going to stick with a white background for this example. I'll close out of that. And then the next thing is we have our toolbar up here. So this toolbar consists of lots of buttons, and these are all tools, and they're all organized, as you can see, within their own panel here. So you can move and organize this toolbar how you would like. If you want to keep it as the default, you can right-click anywhere in the blank space of your toolbar, and you can hit or reset to default. We also have the insert menu up here in our menu bar, and this is where you can access model data and create nodes, lines, materials, etc. You can also create loads within this insert menu up here. Now, if we want to change our view within this work window, we can do that up here in this view section of the toolbar. If I want to maybe get a side view of either the XZ plane or the YZ plane, we can do that. We can also look at the Z direction, so we can get a top-down view. And then there's also more options within here, this drop-down menu. and we can view maybe the reverse Z direction if we want to get a bottom view of our structure. We can also set our structure to an isometric view, so we can get a nice clean view of that. And that's also helpful if you need to reset the view of your model. So on the left-hand side here, again, back in our project navigator, we have at the bottom here, under our add-on modules, the list of add-on modules within RFEM. And with the student license, you do have access to all of these add-on modules, which is very nice. These add-on modules are used to design. So RFEM is great for getting the analysis of internal forces and deformations on your structure. But if you want to design something, such as a concrete member or a concrete surface, you need to have these add-on modules. And you don't have to have all of these add-on modules. Let's say you only want to design concrete members and surfaces. You can just simply purchase these add-on modules. But for you guys, they come with the student license. So now we can move on to the tabs down here at the bottom of our project navigator. We have our display tab. So we were in this is the data tab. And under the display tab, here you have lots of customization abilities where you can customize or turn off, turn on anything within the model. So you can see that all these options are organized within these trees, and we can click on the plus to expand these trees. And for example, let's say maybe we want to turn off our members. We can turn off the members and the lines. You have lots of customization within here, and you can go through loads and so on. Next tab is the Views tab. And within the Views tab, you can create visibilities. So let's say maybe you want to view only members by a cross section. So I can go up here to members by cross section, and I can click on these. And let's say I only want to view my 18 by 50 W shape. You can do that easily within this Views tab. And you can see that the visibility is checked on, so I can turn that off. And now I get the whole view of my structure. You can also go up here and you can create or save customized views if you would like, so you can easily access them. Next, we can view results. So I can go up here to my Calculate All button, and this will run a calculation on our structure. Right now, I'm only viewing one load case, and that is the self-weight of the structure right now. So you can see that all my global deformations are being shown right now. I can get an idea of how the structure will handle the self-weight. As you can see on the right-hand side here, we have our panel, and that gives us the corresponding numeric value with each color. And then on the left-hand side here, again, we have our options or data organized in trees. So let's say right now I'm viewing my global deformations. Maybe I want to view the internal forces or the shear on my members. So I can view the shear in the Y direction on my members, and that will give me these diagrams. And you can see I can also change the rendering of this model, so I can get a better view of these diagrams if I want. I can change the view to just a wireframe view, and the red diagrams show negative, so these are compression forces, and the blue show positive forces. So those are the ones in tension. I can also view my moments, and I can view my axial forces as well. So basically, that is the overlay or overview of the UI within RFEM. We'll get more in depth in this with the examples coming up. And now I would like to pose a question or a test. So now this test will launch right now. I'll give you guys about half a minute to answer that. I'll give you about 20 more seconds. Wait for the majority of people to answer. Okay, looks like mostly everyone answered, so I'm going to close the test about right now. And now we can review. I'll share the results. So great, awesome. Looks like everyone pretty much got the answer correct. So the correct answer, or the question was, what is discretization? And the answer is the structure being converted into finite elements. So yep, this is pretty much when a real life structure is modeled and then converted into finite elements. And I'm going to hide the results. And then I just have one more question before we move on to the modeling of the continuous plate. And you should see that on your screen now. Okay, I'm going to close the test. And now we can review. And awesome, looks like everyone got actually everyone got the correct answer. So the question was, what is RFM? Oops, let me share these results for you guys. Question was, what is RFM? And the correct answer was, it is a 3D FEA program for calculating members, plates, and shells, and also solids. So that's awesome. So now we can move on to the continuous plate example. So I'm going to hide that. And now you should see RFM. And I'm going to, up here, if you don't see your project navigator or the table at the bottom, there's two buttons next to your toolbar here. And you can turn on and off the project navigator. And you can also turn on and off the table at the bottom here. I usually like to have the table turned off just so you have more real estate within your work window here. So now to move on to the continuous plate example. The first thing we want to do is go up here to the left-hand side, and we can click on our button up here called New Model. You can also find this under File, and we can hit New. And this will bring up our general data window for us to create our new model. So basically we just have to enter in this information and work our way down. The first thing I'm going to do is create it or enter the name. So I'm going to enter the name continuous model. You can enter a description if you'd like, but it's not required. You can also have your own projects or have RFEM organize your models into project folders if you'd like by creating a new project and checking out your project manager here. I'm not going to do that for this example. And then for this type of model, since we can have it as just a 2D model, I'm just going to keep it in a 3D model, but you also have the options to only create 2D models if you'd like. And then over here, we have our classification of load cases and combinations. So let's say you want to create load cases and combinations automatically based on a standard. You have the option for RFEM to do that for you. Here we have a long list of codes from around the world that you can use. And then basically that is the information that you need to enter to create a new model. So I'm going to click OK. But before I do that, I would also like to mention you can change the units and decimal places of your model at any time throughout modeling your model. So let's say you want to work with, right now for this example, I'm going to be working in imperial units. But if you'd like, you can also change your imperial units to metric. So you can do that by clicking on this folder button down here. And then you can click on metric, hit OK, and then set that as default. And that'll change and convert all of your units to metric. Here you can also change individual units throughout the model, loads, results, and dimensions. And you can also increase or decrease your decimal places as well. I'm going to leave all that as default and leave it in imperial, and then I'm going to click OK. So now you can see that we have our blank work window, and this is where we're going to be modeling basically. So there's lots of different ways you can model. You can use the tables to enter input data if you find numerically inputting your model data more efficient. For this example, I'm just going to use the tools we have up in our toolbar up here. And I'm going to go up here to the left-hand side, and I'm going to go to New Single Member. I'm going to click on this button. And this would be the tool to use if you were going to create your I-beam or members. But first we're going to model the continuous plates. So I'm going to exit out of that. And then I'm going to go to this tool called New Rectangular Surface. So here we're going to click on the New Rectangular Surface button. And then now you can see we have our New Rectangular Surface window right here. And this is where you're going to enter the data needed to create the surface. So first, you can see we have our surface number right here. And then we also have our material. Right now, by default, this is set to steel. And I want to make this surface a concrete surface. And to do that, I can go to this button right here. And this one's called Import New Material from Material Library. I'm going to click on that button. And now you can see this window pop up called Material Library. So here you can see on the left-hand side, we can filter by category group and then standard group. So first I want to click on this drop down and I want to select concrete. And then the material category of concrete I want is just regular concrete. And then the standard group, for this example, I'm going to be using the ACI, but we also have other standards as well, such as the CSA and etc. So I'm going to choose ACI, and then I'm going to make sure I choose the latest ACI standard, and then I'm just going to use 4,000 PSI concrete under here. You can also edit the material if you would like once you create it. So I'm going to click OK. And then you can see the material set to 4,000 PSI concrete. And my option to edit material is right here. So you can edit any of these material constants here, such as the modulus of elasticity, shear modulus, Poisson's ratio, and etc. You can also create a new material if you'd like as well. So now I would like to change the thickness of this material. Right now it's set to 8 inches by default. I'm just going to make this 12 inches. And then I'm going to click OK. So now I'm going to just rotate my grid plane here. You can see that we have our origin at the center. And then you can see that my cursor has the coordinates locked to it. And you can see that this snaps to any of these points on the grid. Now let's say maybe you want to change the spacing of these grid points. You can do that up here under the settings of work plane. So if we click on this button, our work plane and grid slash snap settings will pop up. And you can see on the right hand side here, we have our grid point spacing. And right now this is set to 1 foot by 1 foot. So each of these points is 1 foot by 1 foot away. And you can also choose how many grid points you would like in each direction as well. Right now, this is set to 50. We also have this nifty option called dynamically according to size of manual or of model. And this is nice because if you don't want to worry about how big your grid is, and you just want the grid to change size depending on the size of your model, you can have it do that. So now back to creating this rectangular surface. So I'm going to click on rectangular surface again, and then I'm going to click on OK, and this will bring my modified cursor back up. So now I'm going to rotate the model just using the mouse and keyboard, and I'm going to click on the origin, and I'm going to left click. And now I am drawing my rectangular surface, and I want this rectangular surface to be 32 feet by 16 feet. So I'm going to go 32 feet in the X direction, and then I'm looking at my coordinates and I'm seeing 32, and then I want 16 feet to be my Y coordinate or my height. I'm going to left click, and now you can see that that rectangular surface has been created within this grid plane. Now I'm going to create another rectangular surface 5 feet above this one. So that's going to be here. I'm going to left click, and then I'm going to draw it again and make sure that it is 32 feet high. So that will be right about here. And that looks too high. So what we can do is highlight, double click on the node. I can change this from 44 feet to 36 feet. There we go. So now that our second plate has been created, we can, instead of having to recreate this plate, we can just simply select the whole plate and we can copy and paste our plate. So I'm going to select this plate, and we have a feature called move and copy. So what I can do is I can right click on this plate, and then I can go up here to my move and copy tool. I can also go up here to the move and copy tool in the toolbar. You have to make sure that you have your element highlighted. This is also a good time to mention highlighting things. So highlighting something from left to right is different from highlighting something from right to left. So if you highlight from left to right, this will only select elements within this window. But if you highlight from right to left, it'll select any element that touches the window. So I'm going to highlight this plate. I'm going to go up here to my move and copy tool, and I want to make just one copy of this plate, and I want to move it in the Y direction. I can enter the coordinates where I want this plate to go, or I can also use this button to create a displacement vector graphically. So I'm going to click on the corner here of my plate, and I want it to be 5 feet above this plate. So 2, 3, 4, 5. It's going to go right here. So now that my vector is created, it's going to move it 41 feet in the Y direction, make one copy. I'll click OK. And now you can see that the plate has moved 41 feet in the Y direction, and it's 5 feet above the second plate. So now I want to make all these three plates, and I want the center of all of them to be on our origin. So I'm going to highlight, and then I'm going to click. I want this corner, this left-hand corner of this plate to be on the origin. So I'm going to click on that, and then I'm going to move it down by just left-clicking and dragging. And that's an easy way to highlight and move things within RFEM. It's just highlighting and clicking and dragging. Now we can create the continuous beam, or AKA create the new member. So up here, this button I showed earlier, we can click on new single member. And you can see that now our new single member window has popped up. And again, this looks pretty familiar to the rectangular surface. We have our member number here. And then down here, we have our cross-section section. And this is where I'm going to create my cross-section. So right now there's no cross-section defined. So I'm going to go here to import from cross-section library. And then I want to create a rectangular concrete cross-section. So within this cross-section library, you see we have our rolled sections, built-up sections, parametric thin-walled sections. Today we're just going to be focusing on our parametric massive sections, and I want to make a rectangular section. So I'm going to click on rectangle. And then you can see you have lots of different types to pick from within these cross-section types. And I want the base of my cross-section to be 40 inches. And then the height of the cross-section is going to be 12 inches. This is the same thickness as our plates, 12 inches. And you can see how that, or what the base and height is corresponding to in this graphic here. You can also see that the material is set to concrete 4000 PSI. So I'm going to click OK. And now my cross-section is shown on the right-hand side here. And the start of my member has this particular cross-section. So I'm going to click OK. And now my cursor is ready for me to draw in the work window the continuous beam. So again, I'm going to space this 5 feet away from my previous plates. And I'm going to draw I'm going to left click here, and you can see that there's a line showing you what you're about to draw. I'm going to make this the same length as my plate. I'm going to left click, and now you can see that my rectangular concrete beam has been drawn. Now we can go through, and I want to add a line or a continuous support down the middle of these plates, and I want to add a support to this beam. So let's say I want to divide these lines here. Right now they're continuous lines, and I want to divide them and add a node in the middle of them so I can draw a line down the middle. And an easy way to do that is just to right click on the line. So basically you can right click anywhere within this work window, and you can see you have a list of tools that are easily accessible. These are the tools that you'll mostly use. You can also turn off and on some other options in this menu. And let's say you want to edit an element. You can right click on that element and you'll get different tools based on the element you have clicked on. You can also edit the surface or delete the surface within this menu. So down here, I'm going to start with this line. I'm going to right click on this one line. And then I'm going to go up here to divide line. And you can see under divide line, we have 3 different options for dividing a line. The first option I will show is how to divide a line by distance. So I basically just want to create a node at the middle of this line. And to do that, I want to set the line start at 50% and the line end at 50%. And I'll click OK. So now you can see that this node has been created and the line was split at the middle. If you're wondering the orientation of the line and you're not sure what the start or end of the line is, you can see that when I hover my mouse over the line, there's an arrow here, and that'll show you the member start and member end of the line. So now I can do this for the rest of my lines. I'm going to right click on this line, and I can also do this by going to N intermediate nodes, and I can set this N intermediate nodes to 1. So this will just equally space out depending on how many number of nodes you want to place on your line. So if I just create 1, it'll divide the line and create this node in the middle here. And then the third option for dividing a line is by doing it graphically. So once I do that, you can see here that the coordinate pops up next to my cursor, and you can see I can just place that node anywhere I want on the line, and I can click and divide the line. And then I can right click anywhere in the space, and that will cancel out of that tool. So now I'm going to do that for the rest of my lines. So I'm going to right click, divide line, distance. And let's say, and instead of having to do this for each individual line, I can go up here to the select lines button, and I can select the rest of these lines, and I can hit OK and divide all of those as well. So now we have nodes at the middle of our lines for each of our plate. And now I'm going to do the same thing. I'm going to divide this member. And again, we have the same options. I'm going to do this by distance, and I'm going to make the node at 50% of the member. So now our member is divided as well with a node there. Now I would like to draw a line connecting these 2 nodes. And this is where our line support is going to go, supporting the midspan of these plates. So now I can go up here, and there's a tool next to the new single member tool called New Line. And I'm going to click on that. And now I can draw just a line connecting these 2 nodes. When you draw a line, make sure you right-click outside of it to cancel out drawing the line continuously. I'm going to connect these two nodes here. And now that those nodes have been connected, we can simply add our line supports in as well. I did want to show you also another great option is if you Control Z, you can undo things. And I can also, instead of having to draw the rest of these lines, I can simply hold Control and then left click and drag, and that will make a copy of anything that was highlighted. So I'll highlight a line, Control, left click and drag, and that will create a copy. There we go. Now we can add in our line supports. So if we go up here to our tool, there's one called New Line Support. And we want to make a line support that is hinged. So right now, that's what our line support is set to, is hinged. And maybe let's say I want to create a different line support. I can do that by clicking on this button. And then you can see here that we have our window for customizing our line support. So right now, our support is set in the translational, it's all fixed. So if I check off UX, that means that the support will not allow the structure to move in the X direction. But if I uncheck it, then that will unlock that direction. So right now, all rotation is not fixed and the structure is able to rotate about that support. So this is what we're going to keep. I'm going to click OK again. And now we can apply this line support to all of our midspan lines here. So now you can see this green line along with our green line supports is added. I also wanted to add the support to the edges of our plates. So to do that, I'm going to hold Control, click, and I'm going to add, I'm going to add those line supports to the ends of our plates as well. Make sure everything is highlighted before you click. Hold Control, drag. Now we can add those supports to our outside lines as well. Oops. This one doesn't seem to want to go. No matter, I can just go up here to my tool, click OK, and just add that graphically. I can right click and cancel out of that. And now we would like to, so now that our line hinge supports are added, I would like to add the supports to this member over here. So to do that, instead of adding line supports, these are just going to be nodal supports. So I'm going to go up here to new nodal support. And the first two nodal supports, or the midspan support and the first end support, is going to be a hinge support. So I'm going to simply add that to these two nodes right here and right click. And now you can see we have a hinge support in the middle here that allows full rotation but no translation. And this end support allows full translation or full rotation and no translation. Now we just have to add one more nodal support to the end here. This one's a little bit different. This one is going to be, I'm going to create a new nodal support for this one. This one is right now allowed to rotate about the x-axis. but we don't want that, so I'm going to fix that. So now the member is not allowed to rotate about the axis, which if we did not do this, it could rotate indefinitely and create a stability error within the program. So now that we have our supports defined and all of our model data entered almost, we can now focus on adding the loads to these different elements. So it is important that when we add our loads in that we create a new load case, because every load needs to be assigned to a load case. So to do that, we can go up here to this button up here called New Load Case, and we can click on that. We can also go here on our left-hand side in our project navigator, and we can go down here to Load Cases and Combinations and Load Cases, and we can simply right-click on Load Case and click New Load Case. So now you can see that the Edit Load Cases and Combinations window pops up, and we are under our Load Cases tab here, and the program has created a new load case for us. So this load case, I'm just going to call test and dead load. And I'm also going to put in here that the self weight of the structure is off. So right now that's the title, and the action category of this load case is dead. And you can see that for dead loads, the self weight of the structure is automatically taken into account. For this example, I'm going to turn that off, and I'm going to click OK. So now our load case is created, and you can see that up here in our drop-down window, we have one load case. And now I can apply the loads to the surfaces. So now I'm going to go up here to this tool called New Surface Load. And the load type is going to be a force, and the load distribution is going to be uniform. You can see we have other options here, but for this example, we are going to stick with these two. And then I want this force to be applied in the global related true area. So this is all good. We don't have to change any of this. And now down here is where we're going to enter our magnitude. So the magnitude that's going to be applied to these plates is going to be 210 pounds per square inch. Again, if you're using metric, you can change the units down here to metric, and you can switch between imperial and metric at any time, and everything will be converted automatically. I'm going to click OK because everything in here is good. And I'm going to click on each one of these plates. And you can see after I'm done clicking on them that our load is being pushed from the bottom up. And this is fine, but for this example, I would like these loads to be applied to the top of the plate. So I'm going to control click on each one, double click, and double clicking on anything allows you to edit elements within the program. So I can easily switch the orientation of these by applying a negative sign to my magnitude. And now you can see that my loads have been flipped upside down or right side up, and now they're applied to the top of our plates. So rotating the structure, you can see that our loads are applied to each plate, and we need to add a load to our continuous beam here. I can also increase the size of these nodes. There we go. And now I can add in a member load. So to create a new member load, this is up here in this toolbar next to new surface load. And I'm going to click on new member load. So also another thing to keep in mind is we have a tool for member loads and a tool for line loads. So just remember that you should use member loads for members, and you should only use line loads for lines. Line loads are basically if you wanted to apply loads to only the perimeter of these plates or to these lines. And then member loads are for members or beams and columns. So this member load window looks basically similar to the plate load window. And under the load type, we have force, which we're going to keep the same. And then we have a uniform load distribution. We're also going to keep that the same. And this load is going to be applied in the global related to true member length Z direction. So all this by default looks good. The only thing we need to change is the load parameters. So again, we're just going to make this load simply 210 pounds per foot. We'll click OK. And now we can apply this to our member. I'm going to right click anywhere to get rid of that tool. And now the load of our structure or of our individual elements here, all of the loadings applied that we need to for this example. Another thing to keep in mind for your structure is the FE mesh, or maybe the FE mesh settings. So normally you don't have to fool with this before you look at your results. But for this example, I would like to show you what having different sized FE mesh looks like. So this first plate here, we're going to have a larger FE mesh. I just noticed here that my line supports are a little messed up here. I'm just going to delete this. And I'm going to add in extra line support at the end here. Right click, there we go. So normally, if you go up here to calculate, and then over here we have our FE mesh settings, you can change the size of the FE mesh right here under general, and this is for the target length of the finite elements. Right now, the size of that is set to 1 foot. So that is the FE mesh that's going to be applied to the whole entire structure. But let's say we want to change the FE mesh of an individual element. We can do this, and I'm going to do this solely just for this example, just to show you what the results, how the results differ for a larger FE mesh compared to a smaller FE mesh. So what I'm going to do is double click on this plate, and this will bring up the edit surface window here. This is nice because if I wanted to change maybe the thickness or material of the plate, I can do that very quickly. And I'm going to go up here to my FE mesh tab, and then I'm going to go to FE mesh refinement, and I'm going to click available. So that will bring up, or that will create a new FE mesh for this whole entire surface. And I can change this FE mesh length to 0.75 feet. I'm going to click OK. And now you can see this icon here has been added to our surface. And this tells us that we have an FE mesh refinement applied to the surface, and also gives us an idea of how large that refinement is with this icon. Next, I want to add an FE mesh refinement to the second surface. And just to show you another way to do this, you can go over here to your project navigator, and where your surfaces are organized, you can see we have 1, 2, and 3 here. I'm going to double click on 2. And under here, again, I'm going to go to FE mesh, the tab here, and I'm going to go to available. And once I click available, right now it's set to the FE mesh we made for the other one. I want to create a new FE mesh refinement. And I want to make this one 0.5 feet. So this one's going to be a little bit smaller. I'm going to click OK. and that icon was added, letting us know there's an FE mesh refinement on that surface. And then I'm just going to add one to this third surface by double clicking on it. So we're going to go to Appear, to FE mesh, and then Available. And I want this one to be even smaller. So I'm going to create a new one for a surface. And then I'm going to make this one 0.25 feet. So I'm going to hit OK again. And now you can see the first plate has the largest FE mesh defined, and it's going to get smaller as we go down the list here. Now I would like to create section cuts before we run our results. Section cuts allow us to get an idea or show us a diagram of results down, and we want this to be down the middle of our plate. So to do this, I can go over here on the left-hand side in the project navigator. And to create a section cut, I can either right-click on the sections category here, or I can also do this up here in the toolbar with this button right here called New Section. And I can create a new section numerically. I'm going to right-click on Section, create New Section, and we have our new section window here. I'm going to name this one, I'm just going to name it AA. And everything else here by default is good. We don't have to change anything. We want our section to go through a surface. We want it to be via plane. And the plane is going to be the local and the local z-axis. And to create the vector or the direction we want our plane to go from point A to point B, we can click on that. And now we can define our section graphically. So since we want to create our section down the middle of our plate, I'm going to click on the midpoint here. And you can see, kind of just like AutoCAD, that the cursor locks onto the midpoint very easily. I can click on the midpoint and then drag it down and click on the other end of the plate. Now that that vector is defined for our plane, I can click OK. Oh, it didn't define my. Let's try that again. There we go. Let's try creating this one more time. I'm going to go over here to New Section. Create my plane vector. Enter my name. So let's try this on a different plate. I'm going to enter my section name. Then I'm going to draw my section vector. And it's telling me that the line, beginning, and end nodes are identical. I believe that my line supports are not defined correctly here. So I'm going to delete that. And I'm just going to define my line supports again. And also check to make sure that these are defined correctly and I don't have multiple line supports on top of one another. I'm also just going to hide these. And now I'm going to create the section cut again. I'm going to draw that. And then I'm going to draw my vector, enter the name. Okay. One more time, it'll be created. So we have our section name, vector, click OK, and now we have our section created. So now I can turn my line supports back on under the display tab. And now our first section here is created on our first plate. So now that our line supports are defined correctly, we have our first section cut. And let's say I want to create, oh, yep, yeah, I can show you that one more time. Okay, so yeah, the section, yep. So basically the section, if you want to create a section cut, you can do that by going over here to the section category, and you can click on new section. And I'll just go over it one more time just to make sure it's clear. So the section name, you can enter up here. It's going to be via plane. And the vector, you don't have to worry about. You want to make sure that you set your first edge point and your second edge point. So point A and point B. And you want to click this button right here. You can define these coordinates here if you'd like, but you can just click this button here to do it graphically. And with your cursor, you can click your point A, and then you can click your point B. And once you do that, you can hit OK. And it's just telling me that the section name is already created. So I just need to make that unique. I'll click OK. And now our section cut is created.
Hey, Alex, I just want to add that the projection vector and what that's used for, that just essentially points the section in the right direction. So I think you're right. By default, that's set to Z in the vertical direction. But if a user wanted to change it into either the global X or Y axis direction, let's say you have a wall and you need to make a section cut through a vertical wall, then you would want to change that projection direction. But that's good for a flat surface, as you just showed. The Z direction by default is correct.
Yeah, oh, awesome. Thank you, Amy, for the clarification. Yeah, so yeah, here you can set that, you can, like what she was saying, you can change your local and global plane here. So for maybe to also clarify, you can also get a look at, we are right now on the left-hand side, we're looking at our global X and Y, Z axes, but each element in RFEM has a local axis as well. And you can see when I hover my mouse over the plates that the local axis is shown. And to distinguish between those, the global axis always has a capitalized letter, and the local axis always has a lowercase letter. So that's how you can tell between those as well. So also to continue, if I wanted to create, maybe I wanted to take the section cut, and instead of having to define it for the rest of these surfaces, I can hold Control and I can left click and I can drag the section cut, and it'll just place that section cut on the rest of my plates. Make sure you hold make sure you highlight it, hold Control, and then click, and that will copy it. So now that we have our section cuts defined here in the local, it's in the projected local Z direction, we can move on to our calculation and showing our results. But before we do that, it looks like we're a little past 2 o'clock. So I would just like to give everyone a 5-minute break if they would like to go get some coffee or use the bathroom. I'll do that. So we'll come back at 2:15. All right. So it's 2:16, so we'll start back up. Oops, gonna open RFEM. So before we get into the results, I would just like to give a quick poll just to make sure everyone is okay with the pacing. Oh. Looks like Julian has a question, maybe? You can ask it in the chat if you'd like, or you can talk as well. I'm also just going to launch this poll real quick just to make sure the pacing is okay. So I'm going to launch this. Oh yeah, Julian. Yep. So yeah, I did forget to mention that this training will be sent to everyone. It's being recorded, so if you want to go back and look at it as well. Thank you. So, yep. Okay, awesome. Looks like everyone answered. I'm going to close the poll and share the results. So it looks like everyone's okay with the pacing. So awesome. So now we can move on to the results.
Hey, Alex, we just have a quick question from one of the attendees just asking if they will get a certificate for the attendance. And I'll just go ahead and comment on that real quick that
Okay.
we will send out both the recording and a certificate for the attendance, as well as all of these models after the training. It may not be today, it'll likely be sometime tomorrow, but you'll have access to all of that information.
Yep, awesome. Thank you, Amy. So now we can go on to the results. Also, these models you guys should also find in the materials section of your GoToTraining panel as well. So you can download those from there. So now that we have everything from last time modeled, we have all of our model data, we have our section cuts. Let's say you want to see your loads again. I did forget to mention that up here. There's a button called Show Loads. So if you're not seeing the loads on your model, make sure this button is clicked. And I usually just keep it unclicked just to have a cleaner look. And then up here, we can click on this button if we just want to see the results for our selected load case. And then, or if we have maybe lots of load cases and load combinations, we can just go over here to the Calculate All button. So I'm going to click on Calculate All. And now RFEM is going to calculate the deformations and internal forces of our elements here. And now you can see right now that we have our results tab here in our project navigator, which wasn't there before. This only comes up if you have results. And right now we're viewing the global deformations. So you can see we have the colored cross section or the colored planes giving us an idea of what the deformation is on each of our slabs here. And again, we have the panel on the right-hand side. If you can't see this panel, you can also turn this on and off up here under the toolbar, just like the project navigator and the tables. So that can be turned on and off. And then you can see on our continuous beam here that our deformation is just shown as this yellow line. Let's say you want to view it as like a colored cross section, kind of like these planes. We can do that by going under here to the display tab, and then we can go over here to our results section. So I'm just going to collapse my model options here. I'm going to expand results, and then under the deformations section right here, I'm going to expand that, and then expand members, and here I can choose cross sections colored. So now that that's activated, I'm going to go back to the results tab, and maybe we want to view the internal forces on our member here. We can turn off global deformations, uncheck that, and I'm going to expand members here, turn on members or results for the members. And maybe I want to view the moment about the y-axis. I can turn that on under internal forces. And now we get this moment diagram, moment diagram that is illustrated on our beam. And you can see that, again, blue is tension forces. And then we have our peak here, which is our compression forces. And then we can also go in and view the internal forces of our plates here. So I can turn those on simultaneously. I can go over here to my surfaces category here. I can check that off. And right now we are viewing the basic internal forces, mx, of our plates. And each color, you can see the value for each color or corresponding color is shown in our panel here. On the side, we can get our max moment and our lowest moment right here. And let's say maybe you want to view a diagram on these plates, just like the one in the member here, to get a better idea of like the peaks and valleys. So we can go over here on the left-hand side and click and turn on our section cuts. And now you can see that we have our peaks and valleys, or our tension and compression forces based on our section cuts right here. And that is giving you a better visual of the moments on our plate here, or our plates. So now you can see the results, and also you may be able to spot the difference in accuracy of the FE mesh here. So you can see that our FE mesh, or our diagrams here, become more accurate as the FE mesh size or the FE mesh size decreases as we go along here. So now is a good time to mention, I think I might have mentioned this before, but FE mesh, the size of your FE mesh does take or affects the accuracy of your results depending on the size. So a bigger FE mesh may yield less accurate results compared to a smaller FE mesh. Just to mention again, looks like there was a question.
Yeah, so we have a attendee asking, I have trouble in viewing the BMD of a continuous beam. It shows the contour. Can you change the size and display result numbers? Oh, that's a separate question from Julian. I'm not familiar with what BMD is. So if you want to clarify what that question is, we can go ahead and, oh, moment diagram. So it looks like he's having trouble viewing the moment diagram of the continuous beam. It just shows a contour. I think maybe, Alex, it has to do with how the results are being displayed for members. Do you know how you can orient, or sorry, you can change the view of members from a diagram to a colored cross section under your results diagram? Maybe you could explain that, and then we'll get into the second question.
Okay, yeah, so basically you can go under the display tab, and then under results, you can go instead of under deformations here, you would have to go under members. And under members, so just to clarify again, results, members, we have options here. So right now I have it set to 2 colored. And you can also change this to colored with diagram. Maybe yours is set to just this, just giving you colors to show you the results on the continuous beam. So if you want to see this moment diagram, then that would have to be checked on.
Yeah, and if there are still questions with that, maybe we didn't address it, feel free to, email us after the model or after the training and send us the model that we can take a look. And then to get into the second question, can you change the size of the display result numbers?
Yeah, so if you're talking about these individual values here, you can change basically the size of any of these fonts. So to do that, I would think the easiest way is just to click on the member and you can right click on it. And then you can go down here to display properties. And within this displays properties window, you can change a lot of different, you can customize a lot of different things within here. Right now we'll just customize the fonts. So we'll go to fonts and then we'll go to results. And then within here, internal forces of members. And then once this comes up, there's a button down here called set font. And then once this is open, you'll have your size window here. And I'm just going to click on this and enter, I'm just going to enter 11. I'll click OK. And then you'll see that the font size is increased. And then you'll see that that font size has increased within the window. So I think that should answer that question for Julian. No problem. Awesome. So I think, yeah, that's all the questions for now. Now we can move on to where we were going into, oh, right, the FE mesh. So just one more time up here for FE mesh, we can go under calculate. And under calculation, we can go to FE mesh settings. And I did mention this before. I'd just like to mention again that you can change the global FE mesh. If you have a large structure, you don't have to change the individual FE meshes. You can just go up here and it'll change the FE mesh of the whole structure. So I'll click OK and everything's good in there.
We have another question. Okay. From one of the attendees. Has the result of the stresses been verified against Rourke's formula for stress and strain? I appreciate the Rourke's formula is primarily for linear analysis, small displacement. Mm-hmm. I don't know that information right offhand. I don't believe that it doesn't strike anything within me that of my knowledge that we've used that formula for comparison, but mm-hmm. Of course we've run many different verification problems. I'm just not sure which theory. So if it's okay, we will just get back to you on that after the training.
Yep. Okay. That sounds good. Thank you, Amy. Then we can move on to the calculation parameters, which we can change within here. So we are going to get into the theory a little bit. Rourke's formula isn't something that we are going to discuss, but we can go up here to calculate, and then we can go up here to, or down here to calculation parameters. So under calculation parameters, once this window pops up, you can see that we can change, we have an option here. There's many options here, but I just want to point out and isolate one option here. This one is called activate shear stiffness of members. So you can turn off this option if you like, This option, I'm mentioning it because this is important. If you're trying to compare hand calculations to RFM, you would want to turn this off because RFM is always calculating with shear stiffness of members. So once this is done, or once this is turned off, you have to click OK, and it's going to ask us if we change something. So this action requires the results to be deleted. I'll click OK. Now the results are deleted, and we can run the results again. And I'm just doing this to give you an example that if you turn off the active shear stiffness of members, it's going to affect the bending moments. So before, our values were different compared to now, if you remember them from before. And the reason for this is because the methods used in school assume that there's an infinite shear stiffness, when in reality there are some shear deformations that go on within these elements. So I just wanted to explain this, so if you're trying to compare hand calculations to this bending moment diagram, then this is an important option to turn on or off. So keep this in mind when comparing hand calcs. Now, I would just like to, so now we can move back to the PowerPoint, and this is where we're going to discuss some plate theory. So
another quick question from a user.
Okay. Yep.
Can we find the distance of the moment change point tension to compression from one of the end supports? I think what's best here is to right click on maybe the member and show the results diagram.
Okay. Yep. So that's a good point. We can right click and show the results diagram. And that is going to open up a new window. So I'm just reading the question one more time.
Yeah, I think it's just inflection points. Just you
Okay.
can see within this results diagrams the distance up at the top. But is it moving for you?
Yeah, 1 second. My computer's catching up.
Okay.
Oh, he or she wants to know it for the plates.
It's exactly the same thing for a results diagram. You can do it either for a member like this or that section cut that Alex had made through the continuous plates. You can also view a result diagram in this exact same manner.
Yeah.
By just right clicking on it.
Yeah, so yeah, this does good. And yeah, inflection points, this will give you more details on those diagrams. You can also turn on and off other diagrams or results here. So I can also show so if you wanted to view that for the plate, you would just have to click on the section cut here, right click on it, and then you can also open up this results diagram as well. So this should come up. And then once it loads, you can see you have your global deformations, moments. This is a load. If you want to see maybe your shear, you can turn that on as well. So that should be down here.
And then we have another question for continuous beams. The thickness plays a great role for thin and thick plates. How do we handle this issue here in RFEM? And I can go ahead and answer that. Yes, it is important, a thin or a thick plate. When we're getting into a surface element its thickness is relatively comparable to its width and its width mostly, then you would want to convert this to a solid element, a 3D solid element. So we have some recommendations in our FAQ of kind of when you need to consider a solid element instead of a surface element in order to get accurate results. But kind of a good way to think of this is a brick element. If you're trying to model something that looks more like a brick, then probably a solid element would be better than a surface. So hopefully that answers your question.
Awesome, great explanation, yeah. Yeah, unfortunately, I'm not getting into any solid elements this this training, but yeah, we do have those FAQs and lots of resources on our website for that. So I do see this other question. How do you change the sign of compression and tension in the moment diagram? So yeah, so I don't think, I'm not sure I don't think you do. So within the diagram, the sign tells you which point is in tension and which point is in compression. Or well, for the moment diagram, it would be your direction of the
So this
bending
is,
moment.
yeah,
Yeah.
and I'll just comment on this. This is based on the right-hand rule. When you're
Mhm.
looking at moment diagrams, you have positive and negative moment, and that's the convention that RFEM goes off of. So you don't have the ability to change the sign within the program. It goes off of the right-hand rule.
Yep. Yeah, the right-hand rule. Yep. That's good. Yep. Yeah. So any more questions before we move on to the plate bending theory? Awesome. If you don't have any right now as well, you can save them for the end as well. So I'm going to go up here and I'm going to change. We're going to go back to the presentation. And we can get into, sorry, one second. So now we can get into some plate theory for RFEM. So this is an analogy for beam elements. And so one of the theories for beam elements is Bernoulli's theory. And another theory is the Timoshenko theory. So for Bernoulli's, these are the two assumptions we make. We assume that the cross sections remain in plane and perpendicular to the member axes. And then Bernoulli's simplifies and assumes that there's no shear deformation. So the whole entire beam is completely rigid and there's completely rigid shear stiffness. For the Timoshenko theory, again, we assume the cross section remains in plane and perpendicular to the member axes. But for Timoshenko, we assume that there are shear deformations that are being taken into consideration, and the whole member is not completely rigid. So to show a good example of this, I have a graphic. And with Bernoulli's, you can see here that the deformation is completely perpendicular to the member axes. And for the Timoshenko theory, you can see that we have an additional angle here. So we have additional deformation. So, and this again is due to the additional shear deformations or shear stiffness that's being taken into account. So these two theories for members or for beams can be applied to plate elements, or not applied, but referenced a little bit. So this is an equivalent analogy for plate elements. For the first plate element theory, we have the Kirchhoff theory, and then a similar theory to the Timoshenko theory is the Resner and Minlin, and this works for plates. So the Kirchhoff theory, you can compare to Bernoulli's theory, and like I said, Resner and Minlin, you can compare to the Timoshenko theory. Now, the assumptions made for the Kirchhoff theory, pretty much the type of analysis is going to be geometrically linear with small deformations. We're using a linear elastic material, Hooke's law, and we assume that the cross sections are flat and not warping. They all have a constant, or the element has a constant thickness, and that there's no consideration of shear deformations, kind of like Bernoulli's. We assume it's completely rigid there. For Resner-Mindlin, the first two are the same as the Kirchhoff theory. We're also assuming there's no warping and it's flat, and that there's a constant thickness of the plate. But for Resner-Mindlin, we're taking into consideration shear deformations, and we're also taking into consideration transverse/lateral strains. And to get a better idea of what transverse/lateral strains look like, we can go on to the next slide, and I have a graphic that helps explain that. So transverse/lateral strain, basically for this example, or for an example, here you can see we have a beam, and when a tension force is applied to it along its length, the cross section over here will shrink with regards to its height and its width. So you can see here that this mu factor is what is taken into consideration, or this is used to take this shrinkage into consideration. And this is what is being taken into account with their Resner-Mindlin theory. So just to summarize, the Kirchhoff theory and the Resner-Mindlin theory for plates. For the Kirchhoff theory, no consideration of shear deformations is taken into account. And this theory does yield great results when you use very thin plates, for example, concrete slabs. And you have to keep in mind that this only considers pure bending, loading bearing capacity, and this is just overall more of a simplified approach. For Resner-Mindlin theory, shear deformations are considered. This theory is great for thick and thin plates. The shear influence component is relatively high for this one, and there is a significant error when neglecting shear force. We also have a higher value approach for this theory, and for shear forces, this one does yield a little more accurate results. So in my opinion, the Resner-Mindlin theory is what you should use probably almost 100% of the time. And it's just good to know the difference between these two theories as well. So now going back to RFEM, we can look at our calculation parameters again by going to calculate and calculation parameters. And you will see that under global calculation parameters, we have down here plate bending theory, and you can switch between the Mindlin theory and the Kirchhoff theory. So right now, let's take a look at the results, and we can see how those change depending on which theory we have activated. So let's take a look at shear. Right now I'm under surfaces, and I'm taking a look at my shear diagrams through my section cuts on my plates. And we got round 2 here, round 2 here. That's kind of consistent throughout these, even with the FE mesh change. So let's say I go up to calculate, and I go into calculation parameters. And that window will pop up, and I can change from the Mindlin theory, which is by default, to Kirchhoff. I'll click OK. I'll hit yes. It'll clear my results because I changed the parameter. I'll hit calculate all. And our results should change, probably not significantly, but very slightly. So yeah, so before we had, it was around 2. So now our shear is a little bit higher now at 2.1. And you can see that those results have changed slightly. So I'm going to go back and I'm going to change that back to the Midland theory. And while I do that, I do have a question for you guys. So that should come up, whoops, right now. And I'll just keep that up for a minute or so. So it looks like the majority of everyone submitted. So I'm going to close the test. And now we can review the results. So it looks like the average score is about 60%. So we'll just go over the question. What happens if the shear stiffness is activated? And the correct answer is shear deformations are considered. So with shear stiffness being activated, this pretty much is saying that the shear stiffness is not completely rigid and it's going to change depending on the deformation. And this is what happens in reality with structures in real life. This is compared to having it off, which would assume a completely rigid shear stiffness. So I'm going to hide the results. And then I just have a second question before we move on to the Euler case 1 example frame. So that should come up right now. Now I'll just give you guys around a minute for that or so. All right, so it looks like the majority answered. I'm going to close the test. And I'm going to show the results so we can view them. So great, looks like the average score is 91%. The question was, the plate Kirchhoff theory considers no shear deformation. And that answer is true. So I'm going to hide the results and close that window. It looks like there's a question from, so I would like to know how the cross-section of members will affect the result. Because we were turning off the self-weight, for example, in this example. Oh, yeah, so for this example, I do have the self-weight of the structure turned off. So if I had this turned on, I think the question is, if this cross-section was larger, then I would have a larger bending moment because of the weight of the beam. So the weight of the beam, or the self-weight, is superimposed with the loads that you apply to it. So if I had self-weight turned on, you could visualize that as a uniform load applied to this member on top of this load that I applied. So the shear and bending moments would be higher. I think that answers your question. Yep, awesome, no problem. Yeah, so now we can move on to the Euler case 1 example frame. So now I can create a new model. I can just keep this one open. Maybe I want to save it. I can go up here to the save button. Models are automatically, not automatically saved, but they are automatically backed up. So if your program crashes or something like that, the model will automatically be saved and there will be a backup. So that's always good to know. So I'm going to click on new model. And this one I'm just going to name Euler case 1. And this one, again, the type of model is going to be 3D. You can enter a description if you'd like. We're not going to generate load cases automatically based on a standard, so I'm going to keep this checked off. And then for units and decimals, I'm going to keep it in imperial units. Again, you can change your units and decimals at any point from this button, and also under the options button or options menu and the program. I'm going to click OK. It's saying this model already exists, so I'm just going to name it example 2. Click OK. And now a blank work area should pop up with my grid here in the XY plane. And now for this example, I'm going to create one new single member. So I'm going to go up here to my new single member button. And then I'm going to create a new cross section. So I'm going to go over here, down here to import from cross section library under cross section. And this cross section is going to be an I-beam. So under rolled, we have our I-beams here, or I-sections. I'm going to click on that. And under I-sections, I'm going to have a W-shape section here. On the left-hand side here, we have our filter again. So we can filter to lots of different standards here. For this example, I'm just going to be using the AISC American standard. Then the manufacturer standard, I'm going to keep as the latest 2015 standard. Maybe I want to filter to exactly a W shape or I section. I can do that. And then on the right-hand side here, you see you have your long list of different W shapes that I can pick from. And if I click on one, you can see it'll give me the dimensions over here on the right-hand side. For this example, I'm going to use a 12 by 35 I section. So click on that. And then the material, you can choose down here. You can click if you want to change this material. I'm going to keep it as CLA 992, but for this example, let's say you want to change it, you can go to the import from material library. And this should look familiar from the last example. You can filter to metal and then category and standard group as well. So I'm going to keep this all the same. I'm going to click OK. And now you can see that under cross section, here we have our I-beam. Maybe you want to get some info about this cross section, you can click on this I button here. And this info section will give you lots of cross-section properties and their values in units. So we can view depth, width, shear area. We can view our moment of inertia. Looks like there's a question. May I know if there will be plans in the future to include the Australian/New Zealand profiles into the library? I think, Amy, would you know that offhand? I'm not sure if you are muted, Amy, or not, if you're still here. I believe, let's see if we have the Australian/New Zealand profiles. I can go under my cross sections in the cross section library. And once that opens up, yeah, I'm not sure offhand if we have those or not. And I can always just let you know later on through email if we're going to add those or if we have them. So yeah, I can find out for you after this. Oh, did you? Okay.
Yeah, I'll comment on that. We do have those profiles. I know we have Australian profiles. If New Zealand follows the same code, then those should be available within directly within RFEM. So.
Okay. Yeah. It looks like he said he or she thinks it's thinks they saw it. So yeah. So we can move on to, oh, looks like I changed my cross section. Sorry about that. Changed my cross section back to 12 by 35. My computer's lagging along here a little bit, so we'll just open this back up and I can change this to 12 by 35. I-beam. Click OK. Now 12 by 35. So now I would like to also demonstrate. So you can see that our grid plane here. Oh, another question from Julian. Is there a way to import codes from other countries to RFEM? So if your country's code, if you're talking about creating load cases and combinations through the code, you can customize and create load cases and combinations, and then you can save your model as a template, and then you can have that template open, and that will be a way for you to save customized load cases and combinations. With regards to cross sections or materials based on your country's code, if you want to do that, you can create custom cross sections. So you can create your own cross section here, and then you can enter in the cross section properties and everything, and you can save your cross section by that. I'm not sure if you can import those. Amy, do you have any insight on that?
There's no way to mass import cross sections into RFEM. It would have to be imported in here individually, but we have quite a large array of cross sections available in the program that if you don't see one of your codes visible, just reach out to us and maybe it's something that we could implement in the future. But I would be surprised as most of them are here. And just as a follow-up, the attendee is just wondering if Doable had add-ons with international codes. So all of these add-on modules within the program, and we won't get into them today, but they provide design for the model. So everything that Alex is covering today is just analysis, and there are codes. You know, for example, many steel codes, as Alex is showing, for many different international standards, including AISC, Eurocode, Chinese, Australian. So that's probably maybe what you're looking for. And again, if you don't see what you're interested in, you can always send us an email. Maybe we could consider it for a future development.
Yep. Thanks, Amy. Yeah, so that's a good explanation. So then, yeah, like she said, I'm not going to get into any of these today, but I am going to go into, within this example, I will just get into the RF stability add-on module. That's not per any design code, but we will get to see at least how like the add-on modules work within RFM. So I'm going to continue creating this member, and if, let's say I want to create this member to the height or perpendicular to this grid, if we want to change what plane we are drawing in, so right now if I drew, I would only draw on this plane. It's only going to be on this plane and not perpendicular to it. I can change my work plane by going up here to this toolbar, and I can set my work plane to the YZ plane or the XZ plane, and I can draw a perpendicular member into the Z direction. So I'm going to put this back to the XY plane, and let's say I don't want to change my work plane, and I just want to draw this column right on the origin. I can go back up to that tool called New Member, and I can check off this option here called Length and Direction, and I can set this to perpendicular to work plane, and then I can go over here to my origin, and let's say I want to make this 30 feet high, this column. I can enter that using my numerical pad, and then I can hit enter, and I can click on my origin, and that will enter that column. And that is, one second. That is not 30 feet high. So I can easily change this. I can just highlight this node. I can double click on the node, and I can make it 30 feet high in the Z direction by editing this coordinate here. Right now it's only 3.28 feet high. I can enter 30. Oops. And it's telling me, okay. Just gonna double click on this node again. Enter 30 feet. Sure. There we go. So now I must have had my origin selected as well. So that's the reason why it was giving me that message. And I'm just going to make sure, yeah, so, okay, I see what happened. Yeah. So I had my origin selected at the same time. I'm just going to delete this top member. And now we have our column that's 30 feet high. So now I would like to add a load. So again, to add loads, or actually, I'm sorry, before we add the load, I'm going to highlight this bottom node here, and we have to add our supports. So I'm going to add a rigid support to the bottom of this column. So this is going to be a nodal support, and I want this nodal support to be fully rigid. So you can see these check marks are telling me that it's fully rigid and fixed in translation and also rotation. So I'm going to click OK. And now you can see that that support has been added to the bottom of my column. And it looks like it's around 3. So before I add in the loads and go through the calculations, I'm just going to give everyone a 5-minute break, and we can come back here at 3:10. So we'll take a quick break. Okay, so It's 310. Okay, so I see the question. I think Amy is going to take care of your question, so I'm going to keep moving on, but no problem. We'll get your question answered along with that. And now I'm going to move back to RFEM. And then we can continue on with the Euler case 1 example. So yeah, don't worry guys, your questions will get answered. And I'm going to apply the load to this column. So first, before we apply the load, or actually we can just go up here, and instead of having to go to create a new load case and combination, we can go up here to new and nodal load, which we can, this is the load we're going to apply to the node. Nodal loads are point loads, So I'm going to click new nodal load, and that's going to bring up, so clicking new nodal load is going to bring up the edit load case and combination because the program recognized that we don't have any load cases yet, and loads have to be assigned to a load case. So this load case I'm just going to name it test, and it's going to be in the action category dead. And again, I'm just going to turn off the self weight, so I'm just going to put in this name here and self weight off, just so we know. And once that's done, I'm going to hit OK. And now we can apply our loads. So the program was smart enough to know that now we want to apply our load. And for this load or nodal load, I'm going to apply a -5 kip load axially. And then I'm going to apply a 2 kip load laterally. So in the X direction, and then the one axially will be applied in the Z axis. And you can see that in our diagram down here. That will give you an idea of what the loads are going to look like. And I'm going to click OK. And now you can see my cursor has a arrow next to it. I can select this nodal load, right click, and I can rotate the structure, and you can see that those loads have been applied to the top column. So now I want to show you something important. And this is very important to know when working with our software, is that if you go up here and we'll run our calculation, and the calculation of internal forces and deformations will be calculated. And if I look at the side view, I can see my global deformation is at 3.78 inches, and that's in the X direction. We can also go over here and view our internal forces of this column or member. And we can get a look at our moments and shear again. And now I want to show you how this linear or first order calculation differs from a second order calculation. So we'll go back to looking at our global deformations. And now I'm going to open up the load cases and load combinations window again. So I can do that by going up here to this button, going to the drop down, and selecting load cases and combinations. And so generally under this load cases tab, load cases are calculated based on a first order analysis, and load combinations are calculated based on a second order analysis. That's just by default, and those can be changed. So under load cases, for example, I can go to calculation parameters, And you can see that the load cases for the method of analysis, we are set to a linear analysis. And you can change this to a second order analysis. So maybe you recognize second order analysis from the phrases little p delta and big P delta. And you can change these. So let's say I want my load cases to be calculated based on a second order analysis. I can change that. And the difference between these two is a first order analysis assumes that the equilibrium of the beam or column is based on the undeformed system, and the second order assumes that the equilibrium, or it sets the equilibrium based on the deformed system. So I'm going to set this to second order. And maybe let's take a quick look at our results again, just to see them. So right now, these are first order results. These are set to geometrically linear. And if we look at our moment diagram let's say we look at our moment diagram for the moment about the y-axis. Right now, our max is negative 60 kips, or no, sorry, kip per feet. I'm sorry, kip feet. And then if we switch this, or switch our calculation method or method of analysis back to a second order analysis, and we can do that again by going under calculation parameters. We'll set it to a second order analysis, and we'll hit OK. You should see, or we should see if we run our results again, that our max moment has increased by 1 kip foot. So keep this in mind, that you will get different results based on different analyses, and the load cases are set to a first order analysis by default, and the load combinations are set to a second order by default. And just to explain again, this is because, so our deformation is larger with the second order analysis, and that is why our moment has increased, because that deformation has increased. So that will give us a larger moment arm, you could say. Another note I'd just like to make real quick is that members in RFEM are determined to be a beam or column only based on, or solely based on, the loads and how they are applied to the member. So in this case, we have a column because our loads are applied axially to our member. If we had a lateral load maybe placed at the middle, that would assume this is a beam, or RFEM will assume this is a beam then. So now I'm going to move on to checking the stability of our structure. So to do this, we can use the add-on module RF stability. But before we get into the add-on module, I would just like to change my loading real quick. So I'm going to double click on my load, and I can double click on that, and this will allow me to edit the load. So now I'm going to change this from 5 kips to just 100 pounds. So I'm just going to make this negative 0.1 kips, aka 100 pounds. And I'm going to turn off this. I don't want a lateral load. I just want to have this negative axial load. I'll click OK. And then you will see our load changed. And once that's changed, the only reason I changed this is just so we can make this structure completely stable. And now I can open the add-on module RF stability. So to open an add-on module, you can simply just go down to this list of add-on modules. And I want to find RF stability. You can see I have a favorites folder where I saved my favorite add-on modules. And I'm going to double click on RF stability. And you can see that the add-on module has popped up, and they are just basically dialog boxes. And RFEM is still running in the background. We're still in RFEM. And so our stability uses the help of eigenvalues and different eigenforms to perform a stability analysis. So just some background, Euler was a mathematician who came up with different cases to show the critical factor along with the critical load and lengths. This is something every stability analysis does. In order to get the different buckling cases, I will deactivate the minimum initial prestress for cables and membranes right here. And then it is also important that we activate the division of straight members. So this is already by default activated when you go into the RF stability add-on module. We can also edit the FE mesh settings for members with this button right here. So I'm going to click on that. And for more accurate division of my member, I'm going to go down here to minimum number of member divisions. I'm going to change this from 2 to 10. And I'm going to hit OK. So basically all these other options are as default, and I'm going to leave everything as default, and I'm going to hit calculate. I'd also like to mention that the load case is set to load case 1. So that's there. So once that calculates, it basically takes all of the information from RFEM, all the internal forces and deformations, and brings it into the add-on module. So now we get a load factor and a magnification factor, critical load factor here. The critical load factor is the amount you would have to multiply the loads in order to get an unstable system. So if I wanted to get an unstable system, or if for some reason I wanted to make the system unstable, I would have to multiply that 100 pounds I have applied to the column by 135 times. Now we do also have P delta activated, or second order analysis activated, so it's not completely linear in that such way. It can also be looked at as the total percent of loads your structure can take, this critical load factor. So then we also, within this module, have our effective length. We have our effective lengths here, and also our effective length factors. And we can also take a look at these results graphically and take a look at the eigenvectors. So if I go down here to my graphics button, I will get a new tab in my panel over here for eigenvector numbers. If we want to get a better view, or if we want to turn the colored cross section on here, we can do that by going to display. And then we can go under deformation, and we can turn on cross sections colored here. So we can just get a better idea of how that eigenvector looks, or eigenform. Now we can also get a better look at the first buckling case or buckling form. So we can take a look at the second buckling case, the third buckling case, and the fourth buckling case. And for this first one, I think it's clear, I think it's clear that the column will first be unstable in the weak axis direction. So the weak axis direction would be perpendicular to the flange. And this makes sense because this is the lowest moment of inertia direction. So we can take a look at our moment of inertia again and see that the moment of inertia about this z-axis here, you can see the y-axis and the z-axis, this moment of inertia is the lowest right here. So we can close this. And Now we can jump back to our stability and take a look at the effective length factors again. I have to recalculate real quick. This should only take a few seconds. And it's back up. So now we have, again, our effective lengths here and our effective length factors. And now I would like to show you what it looks like when the structure is unstable because of the load being too high. So I'm going to click OK. And I'm going to go back to my, up here we have our drop-down window. I'm going to go back to my load case 1 here. And I'm going to increase this load until the structure is unstable. And so I did this in preparation and found that it was unstable at -14 kips applied. So now you'll see, once this loads, once I zoom in and out, you'll see if I run my results here, we have P delta or second order analysis activated. So if I run my results, I'm going to get a calculation error or message, and this is telling me my model is unstable, and I should take a look at the critical load factors and buckling in the add-on module RF stability. I'm going to close this, and if I want to, maybe I get that unstable error, I'm going to turn off the second order analysis. I'm going to turn this into a linear analysis. I'm going to go back to my calculation parameters, turn this back to a linear analysis, click OK. And then I'm going to run my structure in RF stability. So I'm going to go here to calculate. And it's going to run, it's going to take those internal forces, material and cross-section and members and everything from RFEM. And then it'll show me my critical load factors. So you can see my first critical load factor is 0.966, and that is below 1. And so you never want to have any of these critical load factors below 1 because that's telling you that your structure cannot handle the given loads applied to your structure. It can only take 0.96. You could say that it can only take 96% of the given loads. So that is what it looks like when your structure is unstable in RF stability, and that's how you will know. So I'll click OK. And now I would like to pose a question. So that should come up right now. And then I'll just give a minute for that, minute or so until the majority of everyone answers. All right, I'm going to close this test. We can review. And it looks like there's a 33% average. The question was, the critical load factor specifies which factor can be used to increase the stiffness until the structural system fails. So this one is false because it states that the critical load factor is used to specify which factor can be used to increase the stiffness. And the critical load factor is used to know what the loads need to be decreased or increased by. So again, if your critical load factor is below 1, that means your structure can only handle that certain percentage of the loads given. So if anybody has any more questions on that, I can try to clarify that a little bit further as well. So we'll move on to the moment frame. So I'm going to go back to my load case 1, and I'm going to turn my results off, and I'm going to change my load by double clicking on it back to, I'm just going to decrease it to 5 kips. And I'm going to have only the axial load, no lateral loads. I'm going to hit OK. And I'm going to change the height of this column by highlighting my node and making sure only one node is highlighted this time. I'm going to double click on it, and I'm going to change this height from 30 feet to 10 feet. I'll hit OK, and I want to create this moment frame, and the easiest way to do that is to simply highlight my whole entire column here, and then I can simply hold Control, drag, and make a copy of this frame. And then I can create a beam. So I'm going to go up here to New Single Member, and then I'm going to go to Import from Cross-Section Library. And I'm going to go to I sections. And then everything's set, so I just want to go to sections 8 by 15. So the beam at the top of this moment frame is going to be an 8 by 15. My material set is still A992. I'll click OK. I'll click OK again. And now I can draw my beam. Whoops. Let me just get a better view of this. I can draw my beam by selecting and left clicking on the top node here. And I can draw it across, and I can select the node on the top of my second column. And now we have our moment frame here. So now I can run a calculation on this moment frame as well. And that should only take a split second. And now I can take a look at my global deformations. I can see them only in the Z direction if I would like the Z component, or I can just have the result component. And then I can also take a look at my internal forces. So I can take a look at my moments, and right now my moment diagrams aren't being shown. So let me just turn this on. Make sure they're on 2 colored. I'm under deformations. Collapse this tree, members, with diagram. And now we should get, oh, we just don't have, okay. We have no moment here. So let's say we add in that lateral force. Add 1 kip here, click OK. Add to this one too. and then can run our results. I see there is a question.
Yeah, so we have a question saying, is it by default the analysis will segmentize the column into 12 smaller segments? I counted 12 roughly on the string, could be wrong. And this all comes down to essentially just the settings within the calculation parameters of how a beam is divided. For this one, you can place FE mesh along the straight elements. So under FE mesh settings.
Right, yep. I can show that real quick as well.
Yeah.
FE mesh settings.
So you have the checkbox here to activate member divisions for straight members, which are not integrated in the surface. And you can see here that that's set to the target FE length. So that's turned on. So you can modify the FE length with that. So hopefully that makes sense.
And that'll increase accuracy, correct? Right? Yep.
Oh.
Okay.
Yes, that's correct.
Okay. Yep, no problem. Good. Thank you for that clarification, Amy. Yeah, so now we have our moment diagrams here shown with our results. We also had our global deformations here as well. I can show those color cross sections again. And then let's say we only wanted to keep this moment frame in the ZY plane. We can simply we can select our nodes here. Rotate this, select our nodes. I can double click on both of these nodes that are selected, 1 and 2. And then we can keep these, we can add these 2 nodes here, and we can keep the deformations in plane. So translation, I don't want them to move in the X, but I do want them to move in the Y and Z. So I can turn that on and keep rotation all unlocked. Click OK. And then I can run my results again. And then we can also take a look at our stability and make sure that our moment frame is stable. So there you go. Our deformations are in plane. And I can go back to our stability, run a quick calculation. And our stability will give me the critical load factor. So it's well above 1. It's at 81. So we are completely safe with these loads applied. So now we can also again look at the different eigenvalues and eigenvectors and cycle through those as well. So is there any questions so far from anybody? See, there's another question. So is there a rule that if the factor is less than 10, a nonlinear analysis is required?
So I can answer that.
Okay.
I think that there are some conditions within the Eurocode, for example, that if the critical load factor is less than 10, a second order analysis should be run. And then if the factor is less than, I don't know, I want to say 2 or something, then the structure needs to be redesigned. But this is all code specific. And here within the AISC, we do not have requirements that I'm aware of. So it all just depends on which code you're designing to.
Okay. Thank you for that clarification, Amy. So yeah, so right now, this is the end of this example, and the next example is the concrete model. If there isn't any more questions, I can move on to the concrete member or model, but we can take this time right now if anybody wants to ask more questions, or we could have just an open discussion. I'll just start opening the concrete or opening a new model now. And if we want to get into those questions, we can do that. So I'll open up a new model. And I'll just name this one concrete model 2. And with the concrete model, it'll be a 3D model, and it'll be according to the ASC 7, 16. And with this model, we can create our combinations automatically, our load combinations, and everything else we can keep the same by default. So now we have our blank work window, and I'm going to start by making sure the grid points are spaced out dynamically according to the size of the model. My grid spacing for each grid point is 1 foot, so I'll click OK. And then, oops, sorry about that. Oops, turn that back on. There you go, so you should see RFEM again. So for this concrete model, basically we're going to model this simple structure. I can show it on the PowerPoint real quick. And I see that it is almost 3:45, so we're going to be able to just start this model, but we're not going to be able to finish it. But I'll show you what it looks like. 1 second. I'll pull it up. So this is what the model looks like. It's basically a large floor slab and a large ceiling slab with a hole cut out for a spiral staircase. And again, this is the floor slab. We have a support over here because it is connected to an adjacent building. And then we have our concrete columns, along with a window back here for an opening and a rib member acting as a downstand beam. So I'll start off by creating the rectangular surface. So let me go back to RFEM. So I'll go up here to my rectangular surface, and then I'm going to select a material. So right now it's set to COA 992, and I'm going to set it to concrete 4000 PSI. After a while, after using these materials so often, they're just set in here by default. And then the thickness of this floor slab is going to be 8 inches. So I'm going to keep that as default, and then I'm going to click OK. Now the beginning of this floor slab is going to be connected at the origin, and the whole thing is going to be 46 by 40 feet. So we're going to go up here to 46, and in the Y, 40. Click there. Let me check the, okay. So it looks like Amy's answering your questions. Yeah, okay. So now I'm going to move on and create the nodes that are going to act as our bottom of our columns here. So there's multiple ways you can model with an RFEM. I'm going to show you that you can take this node from this origin and just make a copy of it. And I can move this node using the move and copy tool. I'm going to make one copy of the node, and it's going to be moved 2 feet in the X direction and 2 feet in the Y. I can hit enter, and that node is created. Now we can use that node as a basis for laying out the rest of our columns onto this concrete slab here. I'm going to select that node again, and I'm going to make 2 more copies of it. So 2 copies, and the displacement vector, I only want to make 2 copies at 16 feet in the X direction. So I'll click OK. And now you can see that these 2 more nodes in the X direction, 16 feet apart, have been created. And then since we're going to have 4 columns in this row, I'm going to just simply hold Control, copy this node, and it's going to be symmetric to this left-hand side node that we have here. And then I'm going to copy this whole entire row of nodes. So I can hold Shift down, just like in Windows, you can hold Shift or Control down to select multiple things. I must have moved this 3rd node here. I'm going to Control Z to undo. There we go. Oh, I didn't copy it, so hold Control, make sure Control's held down, copy that node. There we go. So now I can select all 4 of these nodes. Oops. And then I can just right-click on a node and hit Move and Copy. And then I'm going to make 2 copies of this row, and it's going to be moved 13 feet in the Y direction. So now you can see that we have our layout of our columns here. And you'll come to learn that the copy and move tool in RFEM, it can be your best friend at times when doing things that are symmetrical like this. So always keep that in mind. And then after that arrangement is done, I'm going to show you that you can also go into your display tab down here in the project navigator. And maybe I want to view the numbering for my nodes and lines and etc. here. So I'm going to turn on numbering. And now you can see that I get the numbering for my nodes, my lines, my surface. And this kind of just gives you an idea of, or just kind of allows you to be more organized with your model data. So now I want to create the walls for my perimeter here. And to segment these lines, I'm just going to divide them to give me the length of my wall. So I can do that by going to divide line, graphically, and then I want my wall to come out from this corner right at this node here. So that's going to be at 12. And then I also want the wall to come out from this node right here to line up with this axis here. So I basically just divided this line here because this is where the wall is going to connect here. So that's one way to divide lines. I just did it graphically. You can also do it with the other 2 options under the divide line tool. And now I would like to create my semicircle surface over here that's going to be the basis of my spiral staircase. So I'm going to go up here, and under the rectangular surface tool here, there's a little arrow that you can click, and you can see that we have a multitude of tools here where you can create almost virtually any shape surface you'd like. I'm going to use the semicircle tool. My semicircle is going to have the same material properties and thickness as my surface here. Another thing to mention is there's multiple surface types and member types that you can choose from. For surface types, the stiffness you can change to maybe an orthotropic stiffness where you can customize the stiffness. Maybe you just want to make a null surface that does not supply any stiffness or rigidity to your surface. You just want it for a reference. You can also use completely rigid stiffnesses to maybe distribute a load onto something like that. So for this, we're just going to keep this standard. I'm going to click OK. And the radius of this semicircle is 7 feet. So I'm going to draw the origin or the center of it 7 feet away from this top node here. So that's going to be at 4640, or no, it starts at 4640 and it goes down to 4033. Now I can draw the semicircle, click again, and then right click to exit out of the tool. So now I have my semicircle here. And so now that our bottom slab is created, we can move on with creating our ceiling slab. So an easy way to do this, since our ceiling slab is basically the same shape as our floor slab, again, we can use our best friend move and copy. So I'll select the whole entire slab, hit move and copy. I just want to make one copy, and I just wanted to be displaced 11.83 feet vertically in the Z direction. So I'll hit OK. And now we have both of our slabs here. I can look at this in isometric view to get a good look at that. And now I want to look at the top-down view, or the reverse Z direction. So I'm looking at this from the top. I can also get a perspective view. So maybe I want to be able to see both my ceiling and floor slab. So there's a question. Can the copy function also include copy load? Assume the loads are already pre-assigned to the model. Yeah, so if I had a load or a point load, I'm just going to apply a point load real quick. I'm just going to make this that. So if I apply a point load, as my computer catches up, I can do that. I'll just make it, I don't know, -1 kips. Click OK. Put a point load there, and then take this out of its perspective view. I can copy that load and select it, and I can either hold Control down and drag this load and just place it wherever I want. And you can also use the move and copy tool to make a copy of the load and move it wherever you want. Actually, this one, let's say I just want to move it. Yeah, so actually, I might be wrong about the copy and move tool. Do you know that about that, Amy?
Yeah, you should be able to use the move copy tool for loads as well.
Okay. So if I maybe just use this, oops. Maybe if I just use maybe if I want to move it this way.
You need to select 2 points.
Okay, yeah, you're right. Yep. So create that displacement vector. If I make one copy. Yeah, so
maybe the move copy tool doesn't work with loads. I thought that it should. Something we'll have to look into. But yeah, the drag and drop works fine for copying loads as well.
Yeah, I think the move and copy tool, the problem might be is it doesn't know. These are
I think you need to add, it's a nodal load. So you need to, if you're going to copy it, you need to copy it onto another node. You can't just copy it onto arbitrary location.
Yeah, yep. So yeah, I would just use the hold Control and then copy. You can also do that for surface loads, and you can do that for uniform or for linear loads as well. So yeah, I wouldn't use, you can just use the control and copy. So, and then, yeah, so now we're gonna wrap up, and and this is a good time for an open discussion or any further questions that anyone might have. I'm going to open back up the PowerPoint. And feel free to ask any questions. And we also, if you can't think of any questions now, you can also email us at our tech support email. And that's at info-us@doable.com. So, question: how to merge two surfaces. So I'm not sure if I completely understand the question.
So I think that if there are two surfaces lying side by side and you're asking how to merge the two together, the best option is you have the boundary lines for the two surfaces that exist. Just click on one of the surfaces and completely delete it. And also, what you can do is to go back and to edit the original surface and choose the different boundary lines. That's our best suggestion. We don't have the ability to select two surfaces and merge with a single option. You can easily just delete one of the surfaces and redefine the boundary lines of the second surface.
Yeah.
We also have another question. Is there a function similar to master-slave command that's available in other software, especially when it comes to modeling floor diaphragm and ties with the building columns? So Alex, this would be referring to the nodal constraints. I don't know if you have the ability just to point that out.
Yeah, so if you're talking about creating nodal restraints, those, I'm trying to look in you can find them in the project navigator, if I'm not mistaken, correct?
Yeah, we can't see your screen though.
Oh, sorry about that. Oh, I thought it was here. Let me switch back to RFM.
Yeah, so under in the project navigator, a little bit further down, right there, is nodal. Yep. Let's see. Oh, sorry, further down, nodal constraints, very last on that list.
Oh yeah, yep.
So you can right-click to create a new nodal constraint. This gives you the option in the drop-down box of either a diaphragm type behavior or equal condition. So diaphragm, you can see the equations listed here, and then the equal condition would just simply be essentially drawing a rigid link between two of the members, but this would be the option of what you're looking for representing a rigid diaphragm.
Mm-hmm. Yep. Okay, yeah, so great questions. Also, another thing I wanted to point out is don't forget to, after this training is over, to fill out our evaluation. So we would love to know how we did and know if there's anything we can improve in the future, pacing, material, questions, anything like that. So if there's any more questions, we have about a minute or two left. We can keep answering them. This was also what Amy was talking about earlier with deleting these surfaces. They just leave the boundary lines and then you can connect them and recreate the surface like that and merge them. So
we have one more comment essentially. Seems like if I need something, it should be in the project navigator. And yeah, for the most part, the project navigator really has most of the elements that you need.
Yeah, I think the project navigator is the most intuitively laid out. You can also, find a lot of things in the insert menu, such as the model data. If you're looking for those nodal constraints, they were also in here. You can find them. Loads, things like that. lots of options up here, lots of different ways you can go through with your model. So yeah. I think that's good. So if there's any more questions that you think of later on, again, you can email us and I'll get back to the PowerPoint. And I think this is where I'm going to wrap up the training. So let me just, so again, visit our website for lots of videos and recorded webinars. We also have newsletters and events and conferences, along with lots of knowledge-based articles. These resources are very helpful when first starting out in RFEM and trying to learn things. You can search for FAQs as well. And if you have any questions, you can email us at info-us@deluba.com or also give us a call at our phone number here. So one last question. Do you have any plan to arrange any future events? Amy, do you want to comment on that?
Yeah, so on our website at delubal.com, you can see all of the upcoming online trainings. Depending on which region you're coming from, you can see what's available. Some may have a cost associated with them. If you're a student, then feel free to sign up for the free student trainings. But again, visit our website at delubal.com, and under events, you should see the online training there.
Yep. So awesome. Yeah, I just want to thank everyone for attending, and I hope you learned a lot, and I hope you all stay safe, and we'll see you later. Bye.